Hi, I'm Willem, and let's talk about automatic translation evaluation. Having an efficient automatic evaluation that knows when it's correct or not is super useful, especially at scale. Automatic metrics give us an estimate of translation quality. For example, this German idiom is translated literally and misses the meaning, so hopefully a metric would give it a low score. In contrast, this is a perfect translation and should receive 100%. You probably know about metrics such as BLE or character F-score. These always require a reference translation, to which the hypothesis is compared. In this work, we focus on trained metrics, which can be either reference-based or reference-free, sometimes called quality estimation. For now, we'll skip the references for clarity, but everything would apply the same way, even if references were present. Sometimes it can happen that the metric is incorrect. Like in this case, it assigned a very high quality to a poor translation. What we would like is for the metric to tell us that this is only a best guess, and that the guess is likely incorrect. In other terms, we would like it to tell us that it has low confidence in its prediction. A typical approach for this is Monte Carlo dropout. We just run the metric many times with some stochastics, such as dropout, and see how much its prediction changes. If it changes by a lot, then we know that it's likely not an accurate prediction. The issue of this approach is that you need to run it many times to get a good estimate of the variance. Also, if you run without a dropout, then that degrades the actual prediction, so the metric becomes worse at the original task. An alternative is to run it 100 times with dropout and then once without dropout, but that then breaks the confidence estimation. Instead, we propose a different training objective for the metric. The first term is a standard loss. The metric is trained to predict a score close to what a human would predict. However, we add a secondary output to the metric, and in the second term, the output is trained to predict how bad the prediction likely is. This is very cheap and doesn't require multiple inferences or any new data. So now, even though the metric gives us a falsely high quality estimate, it also tells us that it has a very low confidence in its prediction. And indeed, by doing this, we don't lose any of the previous metric capability and have accurate confidence prediction. So this metric knows when it's wrong. All of this also requires a single pass, not multiple, like Monte Carlo dropout. That was one piece of the puzzle. Let's now talk about how the metrics actually work. Typically, trained metrics are some sort of transformer-based encoder with multiple layers. At the end, there is a regressor head that produces the final score. What we did was add an extra regressor at the end that predicts the confidence. However, before we get to the final prediction, we spend a lot of computation, and for some simpler inputs, we might not even need all layers. For this reason, we add intermediate prediction heads to each layer. This again is generally cheap, as it's just a simple linear projection as opposed to transformer blocks. And this is useful for early exiting. If the metric knows the correct prediction at the earlier layers, we can just stop the computation there. And we know when the metric is likely to be correct because we attach the confidence prediction to it. And indeed, if we early exit based on the confidence, we get a high correlation with humans than if we exited at constant layer or based on the variance of predictions. Having a cheaper metric that can be used at scale is great, but let's talk about a specific application. When we generate a translation, we can typically get many hypotheses cheaply, such as through parallel sampling or beam search. For each of these hypotheses, we can score them with quality estimation metric and pick the best hypothesis. This gets expensive at scale, with thousands of hypotheses. Instead, we treat this as a multi-armed bandit problem, where arms are the hypothesis and we are trying to find the best arm. By pulling an arm, we request the next layer of the metric to be computed, which gives us a better estimate of the hypothesis quality. This optimizes jointly for quality and cost computation. If we compare it to pre-selecting hypotheses randomly or with the decoder log probability, this approach is much better at selecting the best hypothesis. Thanks for watching this video. We have trained early exit confidence models of Hugging Face, and there's much more details in the paper.